Hello, and welcome to our Facebook feed live from Biosphere 2. My name is Peter Troch. I'm a professor at the Department of Hydrology and Atmospheric Sciences of the University of Arizona. I'm also the Science Director of Biosphere 2. Today I want to introduce you to a unique experiment that is currently taking place at Biosphere 2. But before I do so, let me tell you a little bit about the reason why we do this research and why it is important to society. By 2050, there will be 10 billion people living on Earth. That's 2.5 billion people more than today. Experts believe that 10 billion people represents the maximum carrying capacity of Earth. That means that Earth's natural resources, such as our water resources, our soils and ecosystems, cannot support a further increase in the global population. At the same time, we lose an estimated 24 billion tons of fertile soil per year due to erosion and climate change. It is estimated that 20% of arid lands and 25% of world's productive soils are currently degraded as a result of climate change. The global cost of land degradation is estimated at $500 billion per year, directly impacting the health and livelihoods of 1.5 billion people. These numbers will only get worse with continuing warming of our planet. Society does face a crisis that we need to address before it is too late. Soil scientists around the world, together with agriculture engineers, work hard to find solutions to feed 10 billion people and more. Here at the University of Arizona, we have invested in a unique instrument that is slated to make significant advances in our understanding of how life can restart on degraded landscapes. That instrument is called the Landscape Evolution Observatory, or LEO. We stand right now under one of the three hill slopes that constitute the Landscape Evolution Observatory. These hill slopes are 30 meters long and 11 meters wide and carry a 1 meter deep basalt soil. The LEO was designed to emulate lifeless landscapes, such as recent lava flows on, for instance, the Big Island of Hawaii. How does such a landscape turn into a self-sustaining ecosystem with fertile soils? And once such ecosystems are established, what is their fate under global warming? These are the central questions that we address with LEO. Literally thousands of sensors and samplers above and within the soils of LEO provide us with information about how water, minerals, and microbes interact to create niches suitable for vascular plants to thrive. Every minute, we collect data about how wet the soils are, what their temperature is, how much CO2 is present, and how much water evaporates from the slopes. During rain events, we measure how much water is stored in the soil, how much water seeps out of the slopes, and how much CO2 is consumed in mineral weathering reactions. These data generate information about how these slopes process water and carbon, and how mineral transformations during chemical weathering release nutrients for plant uptake. The current experiment does not include vascular plants, so that we can focus on the biogeochemical processes related to early soil formation when the soil is bare. Microorganisms, such as microbes and fungi, play an important role in these biogeochemical processes. Since the LEO soils start without the presence of nutrients or carbon, the microorganisms that populate the slopes today are autotrophs. Autotrophs are organisms that are capable of assimilating atmospheric carbon and nitrogen to grow. Some are also capable of harvesting energy directly from minerals. We already know that today's LEO soils contain a remarkable diverse community of microorganisms that add carbon and nitrogen to our soils. After a few years of bare soil experimentation, we will start growing plants on LEO. Plants will drastically change the way the LEO landscapes process water, carbon, and nitrogen. Adding carbon and nitrogen through litter fall and root decay will further promote the formation of fertile soils. The type of vegetation that we will grow on LEO will help us address critical questions in ecology. When you recently joined us, my name is Peter Troch. I'm a professor at the University of Arizona and Science Director of Biosphere 2. And we are talking about a unique experiment that is currently taking place at the Landscape Evolution Observatory at Biosphere 2. Our ecosystems that will establish on these slopes will be adapted to a specific climate that we control. That will allow us to observe how these ecosystems respond when we change the climate by, for instance, increasing the temperature or the aridity. These experiments will provide us with the needed knowledge about soil and ecosystem formation and will result in technological advances that will aid in restoration of degraded landscapes. Our mission to contribute to the science and technology of restoring degraded landscapes is motivated by the global crisis that faces society. You too can contribute to our mission by visiting us at Biosphere 2, by becoming a student or citizen scientist to help us collect and analyze data, or by becoming a sponsor to sustain our research. I hope to welcome you soon at Biosphere 2. I thank you for your attention, and if there are any questions, I'm more than welcome, happy to address them.